always helpful to be able to have some kind of an example to work with. So I wanted to do an example of resonance in tubes. Here's what we'll do. We're going to start with a regular tube like this, and I want to give this thing a length. So let's call this thing, we'll go 1.2 meters. Now I want to say, let's find the frequency of the third harmonic. I can draw this thing out first, and sometimes that's helpful just to be able to see it. So I have an open end here, and an open end here, and an open end means I know I'm looking at an antinode on both ends. Open on both ends means I have symmetric boundary conditions. So I could just jump straight to the math on this thing. Maybe I'll do that first. The wavelength for my third harmonic is going to be 2 times L over 3. 3 because it's my third harmonic. The 2L, that's just automatic for this. So I'm going to get 2 times 1.2 meters over 3. 2 times 1.2 is 2.4, divided by 3 is 0.8. And then I know that my wave speed is equal to wavelength times frequency. I'm looking for my frequency. So I'm going to get 340 meters per second divided by 0.8 meters, which is going to give me 425 hertz. And that's my answer. I can draw this thing, so maybe find F3, draw the resonance. I'm trying to go n equals 3. If I go from the bottom to the bottom, so up, down, that's n equals 2. So I'm going to go bottom, top, down, up. I have one wave, or one loop, 2 loops. I've got a half here and a half here. That's my n equals 3 situation. Maybe then I want to say find F1. I can say F3 I know is equal to 3 times F1. F3 is 425, so F1 is going to be F3 over 3, 425 hertz over 3, which gives me 141 2/3, call it 142 hertz. Maybe then I also want to say, from my third harmonic, how much farther do I have to increase my frequency to get to my fourth harmonic? Or at what frequency do I find my fourth harmonic? And I can do that pretty easily too. If this is my F1, I know F4 minus F3 is equal to F1, because F4 minus F3 is 4F1 minus 3F1, which equals F1. So if I want F4, I can say it's F3 plus F1. I know both of these numbers already. I've got 425 plus 142 makes 567. So I'm going to get my next one at 567 hertz. I could also go through this process again and find it. Maybe now I want to say, let's put a cap on this thing and find the frequency of my fifth overtone. So I'm going to draw this thing again with a cap on it. So I want to see what happens when I put a cap on the end of this. I'll keep this tube as being 1.2 meters long. But now there's a cap on the end. This side is open, so I'm going to need an antinode. This end is closed, so I'm going to need a node. And I'll draw that resting line down the middle. Maybe I would like to find the frequency of the fifth overtone. So I want to find frequency of fifth overtone. Now I have an asymmetric case. If I have an asymmetric case, then I'm looking at odd n values. So n, 1, 3, 5, 7, 9, 11. So my overtone number, nothing. 1, 2, 3, 4, 5. I need my fifth overtone, so I need n equals 11. I'm going to say my wavelength is going to be 4L over n. So the wavelength of the 11th harmonic is going to be 4L over 11 is 4 times 1.2 meters divided by 11, and that gives me 0.44 meters, so 44 centimeters is going to be my lambda 11. I said that I wanted to find F11, so let's do that. My wave speed is lambda 11 times F11, so F11 is wave speed over lambda 11. So I'm going to get 340 meters per second divided by 0.44 meters, and I get that my F11 is 773 hertz. So that's how I work with resonance in tubes, and whether it is capped or not.